Yes. Okay, we are recording today. We're talking about chemistry still. This is a periodic chart of the elements. We talked about it last time, right?
Yeah.
And we were supposed to put together on one of those pages in your book, we were supposed to have a model of one of these atoms. And typically I would choose something between 1 and about 20 just because of the size. All right, because the way we make the model is we're going to use M&Ms to make the model. Okay? Yeah. So students are always like, I want the biggest one because they can have more M&Ms, right? So we have to figure out how many protons are in the middle. We can figure out how many neutrons are in the middle by doing a little math.
Yeah, I literally just put the number.
Right. So if we're only going to do protons, then all the information you need is right here. So for calcium, you would have 20 M&Ms in the middle. How many electrons would you have spinning around it? 20. Right? Assuming this is not doing any chemistry at the moment, right? But to find out how many neutrons, I need more information down below at the very bottom of some of these. It tells us the mass, the weight. And if we subtract, like let's say the mass of calcium was 40. I say 40 minus 20 gives me 20. I would have 20 neutrons. So, Cassie, I noticed you have your book open right there. Okay? So look at the numbers. Is there a little number in the bottom of the square of any of those elements? Do you see a number there?
In the bottom of the
Yeah, yeah. So the top of the square has its atomic number. Yeah, see, you don't have the number at the bottom. The number at the bottom tells its mass. So apparently your book doesn't want to worry about neutrons right now. So that's okay. So when we build your model, with the M&Ms, you're just going to use protons and electrons. Those look like they're glowing from here.
Mm-hmm.
Are they glowing?
Are kind of.
Did they crack? Those the ones you cracked?
No. Well, some of these are cracked, but these almost, the tubes inside literally look like they're glowing from an angle. So.
Okay, just because it's the color of the stuff is
Yeah.
kind of fluorescent. Okay, so the kind of things we covered last time, we talked about what is matter. Anybody can tell me the definition of matter? Cassidy.
The space
Anything that
takes up space.
and has mass, right? If it has weight and takes up space, that's considered matter. And the one thing in the room that's not matter? Light. Yeah, light energy coming in. All right, we talked about protons. Those are the positively charged particles in the middle, in the nucleus. Remember, we figured that all out from the scientists who have done studies before. We have electrons. Where are they?
Outside.
Spinning in an orbit.
In the shell.
Right, in a shell, what we call an orbital shell. And they usually show it as circles, but they're really circles plus those little funny figure 8 kind of things, right? So we have spheres and we have those are called S shells, and we have, bless you, we have P shells, and we have D and F shells, which get really bizarre looking. So here's that word shells. All right, we know that an atom is a single one that has protons and neutrons and electrons. Elements means it's pure of that one thing. If I have pure, bless you, gold, then I have nothing but gold in that thing. And gold is a element. Here it is, number 47. That would have 47 protons in there. We're not going to make that one out of M&Ms. Sorry. Yeah. Mendeleev. Who remembers Mendeleev? We talked about him last time. Dmitry Mendeleev. Emma.
I feel like whatever, Bohr was the one who did the atom.
Right, the model of the atom.
Mendeleev was, the guy who organized it.
He organized the periodic chart of the elements, correct. Very good. He's a Russian guy. And then we've named an element after him. It's called Mendelevium. Right, named after him.
Which one?
I don't have the names on here. Y'all's might have the names in your book there. Does it show the name of them?
Nope.
So way far down, it doesn't even show the name?
Oh, it does.
Okay, so Mendelevium is really heavy, so it's really down there in one of the synthetic ones. Synthetic means we made it ourselves in a laboratory.
I think I found it.
Yeah, what number? I don't even have all the numbers on this one.
It's empty.
MT?
Empty. Is it is it red or yellow or
empty.
blue?
Well, that's because my this is probably an older chart than y'all's.
What?
But if it's one of these that were unnamed, see number 104, 105, 106, and these over here that have UN, Q, UNP, those are unnamed. UN stands for unnamed, so it's not named yet. So maybe they named Mendelevium later. Anyway, so also remember the ones over here to the right are nonmetals. This group to the far right, helium, neon, argon, that red group going down there, those are called the noble gases. Those are the ones that don't do any chemistry. Remember the difference between helium and hydrogen? Remember hydrogen exploded and helium does not because it doesn't do any chemistry. Hydrogen's very reactive. The white ones in these white boxes over here are called nonmetals. The blue, yellow, and other ones over here are all metals, types of metals, and they react differently. We're going to look at some of those metals today. So now compounds, right here at the very end, chemical symbols. H2O means I have 2 hydrogens and 1 oxygen, right? That's what a chemical symbol looks like. And here we're going to look at compounds. Atoms can join together with other atoms to become molecules. If atoms join other atoms in a chemical reaction, a compound is formed. Something we've made something new. We're going to do some chemistry today. Okay? We're going to react some stuff together. A chemical reaction is just a rearrangement of the atoms, kind of like a puzzle. Often the individual atoms are quite different than the compounds that they form. I'll show you an example of that here in just a minute. Sodium is you've heard of sodium, right? It's a metal that explodes in water. What? It explodes in water.
That doesn't make sense.
Chlorine is a poisonous gas that'll kill you. But if you put them together, what do we get? Something we put on our lunch every day.
What?
Yep, sodium chloride is very safe. That's my favorite spice.
Isn't chlorine going pole?
Oh yeah, yeah.
Wait.
Yeah, chlorine is bad for you.
Wait.
But it's also very good at killing bugs.
Like,
can you make
salt? I swim in a pond.
It's naturally occurring. Sodium
Is
salt.
it good to open any of your eyes in a pond?
Where does the chlorine come from?
Just bass and perch.
Okay, let me take these questions one at a time. All right, I asked where chlorine comes from. It's naturally found as an element. It's naturally found in the earth. In the ocean, it's usually tied up with sodium. In other words, it's salt in the ocean. Therefore, it's completely harmless. Okay? As long as chlorine is with sodium, it makes sodium chloride. Bless you. In the ocean, we also have magnesium chloride, which is another kind of salt. In fact, we call it light salt. Magnesium chloride.
Yeah,
Potassium chloride is another kind of salt. Yes.
Make salt?
Bless you. Yes, you can make salt in a laboratory. You take your sodium, you take your chlorine, you make sodium chloride. Yeah. Okay, we got to get them. They are really, they react well together. Notice that sodium's a solid here, and chlorine is a gas.
How would you?
If I put it under enough pressure, it'll turn into a liquid. Mariah.
Does most companies that sell salt like actually make it?
No.
Or they get it
Most
from
good question. Most companies that sell salt go and mine it. They find it and mine it. Have you heard of Himalayan pink salt?
Yes.
Guess where they go to find that? The Himalayan mountains, and they dig it out of the side of the mountain, and they put it in it. They grind it up and put it in a jar for you to buy. It's really healthy because it's got a lot of extra minerals in it, so it's really a good salt to choose. Yes.
If you're just walking on the Himalayan mountain, you just find it.
Yep. It's mostly now because we've been using it. It's mostly you have to go like into a cave.
Okay.
Into a cave, you'd see it all along the walls, and people mine it right there. There's also places. Did you know up in Utah, there's a place called the Bonneville Salt Flats. It's very flat. That's where they have the land speed record because it's very flat. It looks like sand, but you go look at salt. It's just salt. And so do you know what that means happened there? There used to be underwater and there was a saltwater lake. You know what else is in Utah? The Great Salt Lake. It's very salty.
rock salt.
Okay, so salt is from normal. It's a normal compound found naturally on the earth, okay? We have sodium, we have chloride. They're together, they make this salt. There's a place in Africa called, in a country called Mali, and a long time ago, the capital of Mali, it's still a capital of Mali as far as I know, it's a place called Timbuktu. And in Timbuktu, there was this giant, very successful kingdom, and you know why they were so rich?
Because they sold
Salt.
Because they sold salt. Why was salt so important? Back before we had refrigerators, what do you use salt for? To preserve your food.
Yeah.
Like jerky and stuff like that. It keeps your food from rotting. So salt is a very important commodity, a very important item for trade and sale. Yes?
What if you put sodium in your pool that had chlorine in it?
Well, if you had pure sodium, it would explode if you put it in the pool because of the water. I'll show you that in a second. Emma?
Oh, another like thing that happens kind of like that, where it makes something that's edible out of stuff that's not, is water.
H2O, because you have H2 and you have O2. O2 we breathe, of course, that's,
Yeah.
but H2 is hydrogen, which we know what happens if a flame gets near it, kaboom, right? Just like the
It
Hindenburg.
explodes in the oxygen.
So it's the chlorine in pools, they're like little pellets.
Uh-huh. Yes,
How do they make
right.
those?
So they've taken that chlorine and turned it. Have you ever been around, do you have a pool? Have you ever been around when
That's
someone's
true.
putting the tablets in there?
Yeah.
And if you get too close, there's a very, very strong smell of chlorine.
Oh, yeah,
That's the
that's-
gas coming off
That's
there.
bad.
Yeah, and it makes you, if you get too close, it'll make you cough and choke a little bit.
It
Right?
will to me.
Yeah.
I have.
But chlorine, we put chlorine in the water to keep bacteria from growing in there. We put chlorine in our water that we drink. You know that, right?
No.
Yeah.
Water, right?
Tap water. Yeah, when you get it out of the tap, there's chlorine in there because it's important to keep the water safe and healthy, no bacteria in there. Okay? So at my house, I put it through a filter
Chlorine.
and get all the chlorine out
We
of it.
actually use well water.
Well water, yeah, probably doesn't have any chlorine in it. You gotta be careful. You probably put it through a filter so no bacteria gets to you. It's easier to filter bacteria than it is to filter chlorine because chlorine is very, very small. Bacteria are very small but bigger than chlorine. Are we good?
Yes.
Let me show you what happens to sodium when you put in a little bit of water.
Whoa.
Oh.
That's just, yeah, it just
Whoa!
explodes.
Oh my gosh.
So that's pure sodium. Do you know they won't sell me sodium? The chemist, because this will happen. It'll cause this kind of thing.
So they don't sell it?
They won't sell it to me. They won't sell it to you. They'll sell it. If this were an actual school, I could buy it through the school. But I would have to show that I had the proper place to keep something like this. We live in a very humid place. What if just the humidity,
Oh.
it might cause an explosion spontaneously.
Oh, I
Okay.
know that. I think I might have a piece of like sodium, maybe.
I doubt it.
Like, maybe.
We have all sorts of sodium chloride. Now this is chlorine. Chlorine is an atom, right? It's an element. So we can see right here, you'll have to believe me that there are 17 protons moving around in there and 17 electrons spinning around there. When it's by itself, it is in the form of a gas. All right, so when that gas is in a beaker like this or a flask right here, you can see it'll start over in just a second. So there's chlorine gas in there. Here we go. They're going to stick a living rose down into the chlorine gas. And after a few minutes goes by, it does speed it up a little bit. The chlorine, it just absolutely just kills this rose. So chlorine gas was actually used as a weapon in World War I. They're going to pull it out and they're going to see that poor flower is just dead.
I feel bad for that.
Yeah. Okay, so chlorine gas was used as a weapon in World War I
Oh, it turned orange.
and it just, because it killed people.
Oh.
Killed the enemy, right? Since that time, we frown upon using what they call chemical warfare. So we don't use it anymore, but sometimes there are bad people out there who might still use it, right? Okay. When you mix things together, you have something new that forms, okay? And we use chemical symbols and numbers to show what the compound is. That's called a chemical formula. The plural of the word formula is formulae. I know it seems like it should be formulas. And in America, we do say chemical formulas because we are Americans. We do that. But the real word, it's a Latin word. The plural of formula is formulae. And we're going to see some of these chemical formulae right here. Does anybody know what C12H22O11 is?
11 oxygen, 22
Yeah.
hydrogen, and 12 carbon.
Correct. It's a hydrocarbon is what this is called. I'm going to guess, I know it's true for me, that probably most of us in this room have eaten this today already. It's table sugar.
Oh.
I had some sugar I put in my coffee.
Yeah.
Nope.
I probably
No
had
sugar?
some.
No
Yeah,
granola for
I
breakfast?
did.
Coke.
Well, there's sugar
Skittles.
like in the food you
Oh.
eat.
Like
Well,
toast even,
And
had,
like
like
a
bread.
lot of food.
Oh yeah,
Like
but
Coca-Cola has a ton of sugar in
I
it.
had a
Yeah,
slice of
Coke.
chocolate.
I
Oh, there's some sugar. Yeah, okay.
and
What about, this has a sodium, Na is sodium, a hydrogen, a carbon, and 3 oxygens. Sodium, hydrogen, what do we call it? So we could call it a name, right? We have a traditional name for it. The traditional name is baking soda.
Oh.
We're going to use some baking soda today.
Yay.
wait, baking.
Would it be vinegar?
What is C9H8O4? Aspirin. It's called acetylsalicylic acid.
Wait, isn't that
Isn't
for
that-
like headaches and stuff?
Uh-huh. Yeah. It came from a tree. It comes from the bark of
Oh
a tree.
yeah.
Somebody would chew on the bark of the tree and it made their
Oh,
headache
yeah,
go
I
away.
remember
That.
Yeah,
but
you
kids
know
actually
that.
should eat aspirin.
Yeah, we get a lot of things from plants. Yeah. So chemistry is so important for these kind of things. All right, so the type of chemical reactions that can take place to form something new is I can synthesize things. I can take one thing, add another and put those together, that would be like H2 plus O2 gives me H2O, right? Then I can decompose. I have a big thing and I can take it apart. I can take H2O and make H2 and O2. Single replacement, I take A, B, add C, I say A goes to C and B is left over. Double replacement, look, I just do a do-si-do. C goes with A, B goes with D, right? We do a little square dance right there. So those are the, and then there's another one, an important one we're going to learn about today, another type of reaction called acid-base reaction. All right, how chemistry happens. Chemistry happens in the outermost electron shells. We call those valence electrons. They're ready and willing and able to do chemistry. Now this is helium, and it's only got the one shell, and it's got 2 electrons in there, and it's full. So how much chemistry does helium want to do? None.
None.
It doesn't need electrons. It doesn't want to give any electrons away. But this lithium has 2 here, plus 1 more all by itself spinning out there. And it would like this next shell to have 8 when using the Bohr model. Remember, the Bohr model is not exactly right, but it's still very useful. So if I want 8 here, it's got 1. What do you think lithium wants to do with that electron? It just wants to get rid of it. It will give it to something else that wants 1. Okay? This is the same thing with sodium. Sodium has 1 valence electron. That's a valence electron. It'll give it away to something. Guess what? I'll show you in a second. Chlorine likes to give it away to guess who? Sodium likes to give it away to guess who? I gave it away to chlorine, right. Okay, so lithium wants to get rid of that. Now, if lithium gets rid of that electron right there, will it still be lithium?
No.
Yes.
Why will it still be lithium?
Because it still has like the correct number of like protons.
Protons.
And stuff.
As long as the protons don't change,
Oh.
we cannot change the protons in chemistry. That doesn't happen. The only way you change the protons of anything is to do physics. And we call that nuclear physics. And the way we can do it happens sometimes naturally in chemistry, if you will, in something called a radioactive element, right? Uranium, plutonium, things like that fall apart naturally.
Wait,
That's how you can change the nucleus naturally through the way God set it up with these radioactive things. Yes.
So there's a show that my grandpa watches, and they're trying to there's energy, and it's radioactive,
Okay.
and so people have gotten bumps on their head because of
Sure. So if you're working with radioactive elements, they send out radioactive energy, including little radioactive particles called beta particles, gamma particles, or alpha particles, and those come out like little bullets, and they can damage tissue. They can cause cancer and things like this. So we have to be careful around. That's another thing I can't buy from the science companies. They won't sell me radioactive materials. How about that? All right, so let's go find now about our sodium. Our sodium is right here. Its atomic number is, y'all look at your chart and tell me what sodium's atomic number is.
Sodium.
It's way over to the left.
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 11.
11. So it's got 11 protons in it. I don't care about the neutrons at this point. Now let's count the electrons. Ready? 1, 2, full. And now 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That one's full at 8. And it's got that 1, so that's 11 out there by itself, right? So sodium is unhappy because it's got that little stray electron out there just not having anything to do. All right, so now look where chlorine is on the chart. Look all the way to the right. Chlorine should be in group 7.
It's 17.
17 protons. It's got 17, but it would like to have 18. So looky there. Sodium says, hey, chlorine, take my electron. I will look now like something that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What number 10? What's number 10 on the chart? Should be neon. All the way to the right, all the way to the far right. Number 10. Is it neon?
Yeah.
Okay,
Yeah.
so that's when sodium says, now on the outside, I look just like neon. I'm happy now. Chlorine takes on an extra electron, and it looks just like, what's next to chlorine? What's right next to it?
Argon.
Argon. It looks just like argon. Now, is it argon?
No.
No, because it still has what in the middle? The same number of protons in the middle. You get it? But on the outside, it looks like that one in the final column. That's everybody's goal here, gang. On your periodic chart of the elements, The goal of every one of those elements is to look like that far right column. Helium, neon, argon, what's next? Krypton. They get kind of radon, by the way, is radioactive. So okay, so if they can look on the outside, on the cloak of the outside electrons, the valence electrons, like one of those guys in that final deal, then they're really, really happy. Okay, so all molecules and elements want to achieve a full outer shell so they look like a noble gas. They can do this by one of three ways. They can give away electrons like sodium did. They can take electrons like chlorine did. Or they can share electrons. That's what happens with H2O. That's called a covalent bond. They're sharing electrons. So right here we can see now that sodium has given away an electron over here to chlorine. It now has an unbalanced. It has more protons than it has electrons. So it takes on a positive one. It has a positive charge. It's called a sodium ion. Chlorine has taken on an extra negative charge. It only has the same number of protons though in the middle. So it's got a negative ion or a chloride ion. This is called a cation and an anion. Okay. When electrons are gained or lost, atoms gain or lose a charge. The newly formed charged particles are attracted to one another like a magnet. This attraction is called an ionic bond. So ionic compounds usually form crystals. We know that about salt, right? It forms crystals. Yeah. So when they're kind of drawn together by magnetism, because the negative and the positive are attracting each other, then we get that thing that tastes kind of salty. We can even put it in water, right? And it'll still taste salty. It's still there. We're not separating them. Now that we have the ions, we don't have explosive sodium that explodes in the water, or we don't have gas chlorine that kills poor roses. Yes.
If you swallow sodium, would you explode?
It's bad. Don't do that.
That's really.
That's why they don't sell it to you.
If you quickly wanted to die, then.
Yes.
That would be a way to commit suicide.
Yeah, we're not going to be talking about
Yeah.
that. All right. Now, when atoms share electrons, it's known as covalent bonding, and it's a little tighter of a grip. All right. So, because the ionic bonding is they can be separated somewhat easily, but they're still, still ions, and they'll come back together when they can, like a magnet. Here we actually have sharing, so it's a little stronger bond right here. So now in this particular case I have oxygen, which oxygen, what number is it? It's 8 or something. Is it 8?
8, yes.
All right, so it's got 1, 2, 3, 4, 5, 6, 7, 8, and it would like to have 10. So when they come together, we will share these 4 electrons. So at any given time, this oxygen thinks it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this one thinks it has it. So that's a sharing going on there. And in this case, it is sharing equally because they're both pulling at the same kind of strength because they're both the same size. But other times we'll see when there's a sharing taking place, sometimes the sharing's a little uneven. In water, for instance, oxygen will hog the electrons and hydrogen only gets it now and then. And that allows for a very important property of water.
It's like glasses.
So what are acids and bases? Acids form hydrogen ions. So if a hydrogen has one little electron out there and one proton and it gives that electron away, it's just a positive charge, right? It's just a proton out there. If hydrogen gives away its electron, it's just a floating proton, positive charge. That's called a hydrogen ion. Yes?
What's the difference between oxygen and air?
Air has more than just oxygen in it. Air has a bunch of nitrogen, oxygen, argon, CO2, H2O, all of that in there. But our body only uses the O2, the oxygen, for the process in our body. So the air is a mixture of gases, and O2 is one of those gases. All right, so bases form, so we have acids and bases. Okay, so acids form hydrogen ions. So right here, that's called our acid part. So this is called an acid. And then bases form hydroxide ions, which is an OH with a negative charge on it. It's called hydroxide. Acids are known for tasting sour. We eat lots of acids. We like the taste of acids. You said Coca-Cola, it's acidic. That's one of the reasons we like it, because it's acidic. You ever had, Sour Patch Kid things or one of those weird things?
Skittles.
Sour Skittles. All those things are acidic and we like the taste of them. if we eat things that are not acidic, they're more basic, they tend to have a bitter taste. And we're not as crazy about bitter things. Like Brussels sprouts. You know,
I love
asparagus.
Brussels sprouts.
Do you really? I only started liking
Yes.
Brussels sprouts when I was like 50. I didn't like it before that. I like them now.
Who doesn't like?
I like all
Bases, however, I want to tell you also, gang, another word for base, okay, is called alkaline. Alkaline. So we're going to see that in the video here, but I just want to make sure you understood that. So I have sodium hydroxide. When they dissociate, I have hydroxide, which is a base, and sodium, which is, they're both, see, that's an ion. It's got a positive charge. This one has a negative. This took the extra electron. It's OH negative. And this hydrochloric acid has a hydronium ion formed, or a hydroxide ion. Okay. Weak acids include lemon juice and vinegar. Typically, if you put salad dressing on your salad, you're going to have an acid in there, especially if you use Italian dressing or something like that, because there's vinegar in there. I use like a balsamic vinegar thing. I like vinegar. Lemon juice, if you like lemonade. It's acidic. It's nice. Hydrochloric acid is a very strong acid. It's found in our stomachs. It helps us digest our food. Our stomachs are designed so beautifully that this very strong acid doesn't bother our stomach typically. But if I were to take a drop of it out of my stomach and put it onto my skin, it would burn my skin. That's how acidic it is. Okay, it's very strong. The only reason it doesn't burn our stomach is because of the special lining in the stomach. Very strong acids are known as corrosive acids, which can dissolve metals. In my chemistry class, we actually do that. We dissolve some metals.
Can that
Yes.
stuff in your stomach get off of there?
If there's a problem,
Okay.
right, a little hole or something. Have you ever heard of somebody who has a stomach ulcer?
No.
Ulcers when they have a little disturbance in the stomach and the acid starts to eat into their stomach wall. Very painful, and they have to go usually take medications to get it fixed. Yes.
So Dr. Pepper doesn't like take away rust or something?
Oh, it's very acidic. All soft drinks are very bad for your teeth. In fact, all soft drinks are terrible for you. Yeah. So, but it doesn't mean you should never, ever, ever drink a soft drink.
I like Dr. Pepper.
I used to. Now they're too sweet for me. All of them are too sweet for me now.
Sprite. That's it.
Sprite, yeah, that's still acidic though.
Dr. Pepper.
They have acid and they have sugar. And so what happens is the acid bores into your teeth and the sugar gets in there and it gives you cavities. So that one of the and they say Dr. Pepper's one of the worst. The dentists can't stand Dr. Pepper.
I thought Monster was the worst.
Really? I don't know for sure. Weak bases include baking soda. We use that all the time. If you ever bake cookies, you probably put baking soda in there. Helps them rise up just a little bit. Yes, yeah, okay. It's kind of like yeast actually. Strong bases can also be dangerous. Clorox and ammonia are considered strong bases. All right, and if you get in contact with those, whew, they can hurt you. Just like a strong acid can hurt you. Bases that dissolve in water are called alkalis. Just remember the word alkaline is also referring to a base. Acids and bases are opposite of each other. And in fact, when we react acids with bases, we end up doing something to that acid and the base, and it's called neutralizing them. We neutralize them. We're going to do that today. All right, we have something called the pH scale. It indicates relative acidity. In the middle, in fact, I'm going to play a video for you. Let's just watch the video. He'll explain it.
What is pH? Let's start with what it stands for. pH stands for the potential of hydrogen, and it's a measure of the concentration of hydrogen ions in a water-based substance. pH is organized into a scale of acids and bases with neutral right in the middle. The range goes from 0 to 14, with 7 being neutral. pHs of less than 7 indicate an acid, where a pH greater than 7 is a base. But why 7? Because 7 is neutral. One of the first obstacles I had to overcome was remembering which number is neutral, which numbers are acids, and which are bases. So I use Lucky 7, or 7 is heaven on the pH scale, to remember that 7 is neutral. And then I know that any number below is an acid, anything above is a base. I also remember by thinking when you base jump, you jump from a high place. So a base must be a high number. Again, remember, Lucky 7 or 7 heaven is always neutral. Next, let's go through some items that are acidic or basic. Milk is slightly acidic, along with apple juice, lemon juice, and then stomach acid. Some acids can taste very sour. Some examples of bases include eggs, baking soda, ammonia, and bleach. And a base may taste bitter, and it could also be slippery.
Slippery.
Next,
So,
the pH scale has colors that go along with acids and bases. Acids are yellow, then change to orange, then to red. And bases are green, then to blue, and almost purple. Again, remember B for base and blue. So what creates an acid or a base? Technically, pH is calculated as the negative log of a solution's hydrogen ion concentration. But in very simple terms, acids gain hydrogen ions and create hydronium, and bases are created by losing hydrogen ions and creating hydroxide. In very simple terms, acids gain hydrogen and bases lose hydrogen. Each number represents a 10-fold change in the acidity or basicness of the water. Water with a pH of 5 is 10 times more acidic than water having a pH of 6. If you'd like to know more about
okay. That explained all that, huh? I also would say pH kind of like a percent of hydrogens. Okay, using an indicator tells us if something's acidic or basic, acidic or alkaline, okay? So certain substances will turn color. Did you talk about that in that video just now?
No.
Acid base, so I have HCl with a base, so acid plus a base is going to give me water and a salt. Every time, water and a salt. So I can neutralize it by taking my hydrochloric acid, putting sodium hydroxide in there, and I end up with H2O and NaCl. In fact, sometimes when people have acidic stomachs, they take something called an antacid, and it helps to lower the acidity of their
So
stomach.
an ant
Ant being against the acid, antacid. Yes,
What
yes.
happens if your stomach's too acidy?
And then you tend to have, the acid tends to come up your esophagus a little bit, and it causes something known as heartburn.
Okay.
Yeah.
Oh.
Yeah, that's what
acid
A lot of
reflux?
people get heartburn.
Yeah, and it has nothing to do with your heart. It has to do with your acidity of your stomach coming
Feels
up
like
your
heartburn,
esophagus and
feels
kind
like
of burning a little bit, but it happens to be the top of your esophagus, and where it hits your stomach is right near your heart. So it seems like it's heartburn. Did you have a question, Emma?
What about acid reflux?
That's
Is
the same
that
thing.
kind of the same?
Same deal, acid reflux. Reflux means it comes up where it doesn't belong. Okay. So I meant to put half of that in another balloon. Okay, so we're going to do lab now. I'm going to turn this off.